Welcome everyone to 6.5 Exponential Growth and Decay. In this section, we're going to explore some applications of these exponential functions that we've been studying. And then we're also going to recognize that exponential functions are solutions to particular differential equations. And we'll learn more about that actually in 9.3. So, without further ado, let's get to it. So the first thing I have here is a theorem, right? And the theorem states that the only solutions of the differential equation, and this is going to be dy dt equals k times y, are exponential functions. So this differential equation says that the rate of change, the derivative, is proportional to the function itself. And the exponential function should look like y of 0, so this is the initial value of y, times e to the k t. All right. Now, this has many applications. So one of the applications is for population growth, right? So population growth, where P of t is the size of the population at time t, well, then we can write a differential equation. And the differential equation should say that the rate of change of the population is proportional to the population itself. Well, what does that mean as far as equation, right? So the rate of change of the population is the derivative, is proportional to the population itself. So that means if you have more people, there's going to be more people making babies, essentially. All right, so what we can do here is actually solve for k. And if we wanted to solve for k, well, we divide by p. This is a constant, and it is sometimes called the relative growth rate. Now, if we say that the population at time 0 is p naught, or p sub 0 if you'd like, then the expression for the population, right, we can actually solve this differential equation, and we can get that the population at time t should be equal to, now this is going to be the initial population, p naught, times e to the k t. So it looks a lot like theorem 6.5.1 from above. So let's actually try to use this for something. We're going to model a situation here. So we have a disease, and it's reduced by 20% by each year. There's initially 10,000 cases today. How long will it take to reduce the number to 1,000? So let's use our calculators really quick. I just want to guess, right? So today, right, we have 10,000 cases. 10,000 cases. And so a year from today, there should be 0.8 of those. So 0.8 times 10,000, so that's 8,000. And now the next year, so in year 2, right, there's going to be 6,400, right? We times by 0.8 again, and then times by 0.8 again. So after 3 years, 4 years, and we can keep on doing this, right? There's always 80% left over, right, because it's reducing by 20% of the previous year. So it looks like right around, I believe this was right around 11, between 10 and 11, right? So 10 was 1,073, 11 was this 858. So somewhere between 10 and 11 years, that's when the disease is at 1,000. So let's see, using math now instead of just guess and check, let's see if we can get that answer. So according to this theorem up above, well, the population should be 10,000, the initial population, times e to the k t. Okay, and 1 year later, so let's plug in this information that it reduces by 20% each year. So 1 year later, it should be at 8,000. So 8,000 should be equal to 10,000 e to the k times 1. So t here is going to be in years. Okay, so now I can solve for what is this relative growth rate? What is my k value? So if I divide by 10,000, well, a lot of stuff cancels out, and we actually just get 8/10, or the same thing as 4/5. And this is my e to the k. So now if I take the natural log on both sides, well, I get k is equal to the natural log of 4/5. So now I can take that and I can plug it back into my equation, right? And ask, when is this equal to 1,000? So 1,000 is equal to 10,000 e to the kt. My k is the natural log of 4/5. So I can divide by 10,000 on both sides. So I get 1/10 is equal to e to the natural log of 4/5 times t. And again, I'm going to apply a natural log to both sides to get rid of this exponential. And this is going to give me the natural log of 1/10 is equal to the natural log of 4/5 times t. And I can solve for t just by dividing by the natural log of 4/5. And now if I was on a quiz or an exam, this is how I would just leave my answer. But since, we have our calculators, let's go ahead and plug this in really quick and see what it comes out to be. So the natural log of 1/10 divided by the natural log of 4/5 is equal to 10.3, I'll say 10.32 years, since we're rounding. So yeah, this makes sense with what I had intuitively calculated out before with just kind of a guess and check model. Okay, now another application that we can have besides population growth is something like radioactive decay. So some radioactive substances decay by spontaneously emitting radiation. So m of t is going to be our mass remaining from an initial mass, m sub 0 or m naught. And this is modeled by a differential equation. So the derivative is again proportional to the amount that we have, but in this case k has to be a negative constant. So we're decaying in this case. With the population growth, it could be positive or negative because the population might be growing or decreasing. So, and this is going to be the same thing. Solve it. We get m naught is equal to e to the kt. So let's try applying this here. We have a element x and it's decaying. So 7 days ago, my sample had 100 grams. Now we're at 90 grams. And we want to know, when will it weigh 45 grams? So initially, what it is right now, my m naught, or m sub 0, is 90 grams. And again, I need to figure out what is this k value, right? So the first step is always to kind of solve for this k value. So I know that 7 days ago, time is -7, I had 100 grams. So I'm going to use this to solve for k. So let's divide by 90. And let's take the natural log of both sides. And then finally, to solve for k, I need to divide by -7. All right, now that I have this, I can actually solve for how long will it take to give me 45 grams. All right, so let's do 45. The amount that I want is equal to the initial amount times e to the kt. So k in this case is my natural log of 10/9 divided by -7. Now I'm going to divide by 90 on both sides, right, to isolate this exponential. So that's going to give me 1/2 is equal to e to the kt. And again, I'm going to apply a natural log on both sides to get rid of this exponential, right, because we know logs and exponentials cancel each other out. And now I need to solve for t. So I'm going to multiply through by -7, and I'm going to divide through by the natural log of 10/9. And now at this point, I'd be a little bit worried, right? Because I see that time is negative. I see this -7, and that makes me concerned. But in all reality, we have to remember, right? So the natural log of 1/2, right? When you plug in a value that's less than 1 into the natural log, it spits out a negative. So actually, this natural log of 1/2 is negative. So we have negative times a negative is positive. So crisis averted, right? Another way we can, of course, do this because we have our calculators is let's check, right? So I'm going to plug in my -7. I'm going to multiply through by the natural log of 1/2. The claim is that this actually is a negative, and divide by the natural log of 10/9. And we should see that we get out a positive. Yeah, we do. And great, that's positive. And so it's about 46. So I'm going to say 46. And remember, my unit for time here was days, right? So it's 46 days would get me to 45 grams. Now what we did up here was actually we calculated out a half-life, right? We started off with 90 grams and we went down to 45 grams. So physicists are often interested in the half-life of an element. And we could solve this. Half-life is the negative natural log of 2 divided by k. Or, as we can see from up above, right, we could treat this negative as an exponent, right, using the power rule. So this would be the natural log of 1/2 divided by k. And now let's go up here really fast. In our answer, our t, our time for half-life, there it is, and that is our k. Right? We solved for k before. So our answer is consistent with this formula here. All right, so the last application we're going to go through is called Newton's law of cooling. And so it states that the rate of cooling, so this is going to be a derivative, the derivative of the temperature with respect to time, is proportional, so is equal to k times the difference between an object and its surrounding. So the object and its surrounding. So the surrounding temperature is going to be T sub S, surrounding temperature. We have time T, and our capital T is temperature. If we solve this differential equation, the claim is that we get the temperature of the surrounding plus the original temperature minus the temperature of the surrounding times e to the negative kt. And we will actually see in the next video how we can solve for this. So in the meantime, though, let's try to apply it. So in this example, it seems like there's been a murder. The temperature outside is a constant 65 degrees, and they discovered the body at 9 a.m., I would suppose. The body's temperature is 82 degrees Fahrenheit at that time, and then an hour later at 10 a.m., it's 80 degrees Fahrenheit. We have a suspect, Nathaniel Nutmeg, but he has an alibi from 9 p.m. to 2 a.m. last night, and the question is, could he have committed the murder? Okay, so why don't we try to use our formula that we have up here and try to start plugging in some of the things into the right spot. So temperature at time t is going to be equal to, now the surrounding temperature is constant at 65 degrees Fahrenheit. Then we have plus the initial temperature we're given is 98.6 degrees Fahrenheit. Minus, again, the temperature of the surrounding, that's the outside temperature, 65. And then e to the negative kt. Okay, so I'm going to pull out my calculator really quick. I probably don't need to, but just to make sure. Let's see, we have this 98.6 minus the 65. Obviously, I'm just being lazy here. That's going to give me the 33.6. Good. And I'm not even going to pretend this problem right here is really, I made this problem to be done with a calculator. So this would be a difficult problem for on a quiz or an exam for sure. Okay, so let's set up some times here. So I'm going to say, right, we don't know how many hours after the murder 9 a.m. is. So I'm going to say 9 a.m. is T1, T sub 1 hours after the murder. And therefore 10 a.m. is going to be T1 plus 1 hours after the murder. And my goal is to try to figure out how many hours after the murder is 9 a.m. So I want to solve for T1, and if I can do that, then I've done a great job. So let's try to plug in some of this information into our formula here. So we know 9 a.m., T1 hours after the murder, the body's temperature was 82 degrees. So 82 is going to be equal to our formula with this negative k, but instead of t, this is T1 hours after the murder. And then at the second time, at 10 a.m., the body's temperature was 80 degrees. So now this is going to be negative k times T1 plus 1, and that's the entire quantity. So now, like I said, let's use our calculator to start solving for this, right? I'm trying to solve for T1, if at all possible. Usually I have to solve for k first. So let's go ahead and subtract the 65 from the other side, and then we'll divide by this 33.6. So we get 0.506 is equal to e to the negative k T1. Play the same game here, but now with 80. So 80 minus 65 divided by 33.6. And that's going to be equal to our e to the negative k times the quantity T1 plus 1. And now I'm going to apply a natural log to both sides. So with the natural log of 0.506 is going to be this negative 0.613. And when I apply a natural log to the right-hand side, these cancel out, and I just get negative k T1. Do the same thing to the second equation. So the natural log of 0.446 looks like negative 0.8065. And then I'm going to go ahead and distribute that negative k. So this is going to be negative k T1 minus k. And the idea is now I have a system of equations, and if I subtract the second equation from the first equation, you can see that those negative k T1s, they will cancel. How great. So on the left-hand side, it looks like this comes out to 0.1251. And then on the right-hand side, minus negative k is going to be just k. So I was able to successfully solve for k in this case. Okay, let's go back up to that first equation. That first equation makes it pretty easy to solve for T1. So all I need to do is take that negative 0.6813 and divide by negative k, and that should give me T1. So let's take that and we'll divide by our negative 0.1251. And so we get T1 is 5.44 and change. So 9 a.m. is 5.44 hours after the murder. So think about this, 6 hours after the murder. This is a longer time. That would say that the murder happened at 3 a.m. if it was 6 hours. So since it's less than that, it actually happened after 3 a.m. And since he only has an alibi up until 2 a.m., yeah, technically, he has over an hour to go and commit the murder. So yes, the murder occurred after 3 a.m. So this doesn't say that he definitely committed the murder. It's just saying it doesn't, excuse him. Okay, and that's the end of this problem. Whew, that's a long section, but we're finally done. Go ahead and take a break before starting the next video in 9.3, which is about separable equations and how actually to solve some of these differential equations. And we will need that for your upcoming homework assignment. So I'll see you next time in 9.3.